Well, here we are, my friends. It is that time of the day in which we are about to jump into the next live talk. Okay. Well, there's a couple of announcements that I want to make sure are out there for all of you who are just wondering about some really important things. So first, I did just announce the RubyConf 5K or 30-minute exercise challenge. Check that out in the open chat if you have not. This is very important. I hope to see you participating. The other thing is there's an ever-growing list of amazing Slack channels around various topics. One of which I want to call out just because I think it's fun is the Great RubyConf Sandwich Make-Off. If you're interested or want to know what the heck any of that is about, don't forget to check out that channel too. And also, we had heard from the facility manager that there's been some crowding in the kitchen. The current facility has got a lot of crowding, hallway traffic, sometimes blanket couch crowding, and there's a slew of furry friends that are just making their way into the conference without a ticket. So not to say that that's bad, and we welcome everybody, of course, but it's really important to remember that, be nice to one another in your facility, I mean, like, if you're going to make a sandwich or you're going to make breakfast or coffee, like, it's okay. The talks are recorded. You can take your time. You know what I'm saying? So without further ado, here we go. I would like to introduce our next speaker, Emily. Emily, if you want to join me on the stage. And
Hello.
Here we are. All right. Well, good. With that, without further ado, to all my conference friends out there, Emily, it is all yours.
All right. Hello, everyone. Thank you so much for coming. My name is Emily Giurleo, and this talk is called The Bug That Forced Me to Understand Memory Compaction. So in this talk, I'm going to tell you a story. And it starts with a job that I had until recently working at MongoDB. At MongoDB, I helped maintain 3 fairly popular gems, the MongoDB Ruby driver, Mongoid, and the BSON gems. So the BSON gem, which is the resident troublemaker of this talk, is a Ruby gem with a C extension, which is going to come back later. And this gem basically just serializes data to and from BSON, which is the data format that MongoDB uses to send information. That's not super relevant, but it will come back later. So one day, I was going about my business when I received a user-submitted ticket. The user said that the BSON gem was segfaulting whenever they called gc.compact. Now, I am a fantastic gem maintainer, and so my first reaction to this ticket is, what the heck is gc.compact? Clearly, I had a lot to learn before I was ready to fix this bug. And so this talk is the story of how I gained the knowledge that I needed. In this talk, I'm going to teach you everything I learned about how Ruby manages memory, starting with what memory actually is, to how Ruby implements garbage collection, and what memory compaction is all about. Then, we're going to talk about how this gets more complicated in C extensions, and finally, how I managed to fix the bug. There should be about 5 minutes at the end of this session, if anybody has any questions, but I'll also be answering questions in the Slack channel for this talk for the rest of the conference, so feel free to join me in there. Let's get started. So back to my original question. What the heck is gc.compact? So gc.compact is a new method introduced in Ruby 2.7, and it does something called memory compaction. Now, if you are a fantastic gem maintainer like I was, you will ask, but what is memory? And why would you want to compact it? So clearly, I had to go back to the basics if I wanted to get anywhere with this bug. Memory is where your computer stores information. And there are many different types, but for the purpose of this talk, we're going to talk about RAM, or random access memory. So RAM is like the short-term storage of your computer. It's where your computer keeps all of the information that it's going to need for the next little while in order to run the programs that you are currently using. Ruby uses a section of RAM called the Ruby heap to store the data it creates while it's running a program. The heap is made up of many slots, and each slot is about 40 bytes. And slots are organized into heap pages, which are about 16 kilobytes. You can think of the Ruby heap as being made up of many of these heap pages. Every time your Ruby program creates an object, it takes up one slot in the heap where it stores the data for that object. That's not like entirely true, but for the purposes of this talk, it is true. And it's also important to know that every slot has an address, and this is going to be really important later. So as your Ruby program runs, it's going to use up more and more memory in the Ruby heap. Once it uses up all the allocated memory, it's going to create more heap pages that it can fill up to continue running the program. However, memory is a physical component of your computer, which means that it's not infinite. Eventually, it's going to run out. So Ruby needs a way to reuse the same memory to make your program as efficient as possible. And this process is called garbage collection. You can think of garbage collection as the Marie Kondo of the Ruby language. Ruby keeps track of all of the objects that you've created while running a program. And once an object is no longer being used, meaning like it goes out of scope, it's not referenced by any other object in your program, Ruby is going to destroy it and free up the memory that that object was previously using. The Ruby garbage collection algorithm is called mark and sweep. There are a lot of variations of a mark and sweep algorithm, so I'm going to go over it like at the highest level. But essentially, this is what's called a tracing garbage collector because it uses the traces between object references in order to properly garbage collect the objects in your program. So on the left, I have a representation of the heap, and on the right, I have a representation of objects in Ruby and their relationship. So the first part of mark and sweep, I'm betting you could guess this, is called the mark phase. During the mark phase, the Ruby garbage collector marks all of the Ruby objects that are still in use by the program. And that just means essentially like flipping a bit so that each object has that mark that it's still in use. It starts out with marked root objects. So these are objects that are going to be like long-lived in your program. They're going to be used throughout your program. And so the Ruby garbage collector knows that they are still in use. Then the Ruby garbage collector is going to find all of the objects referenced by those root objects, and it's going to mark them as well. So in this example, it would also mark the blue object, which is referenced by the yellow object, and then it would mark the gray object, which is also referenced by the yellow object. If the blue and gray objects referenced other objects, those would be marked as well. And you'll notice that the green object here, it isn't a root, and it's not referenced by any other object, and so it doesn't get marked. And that brings us to the next phase of mark and sweep, which is, you guessed it, sweep. During this phase, the Ruby garbage collector goes through all these objects again and finds the ones that aren't marked, which means they're no longer in use in the program. So since an object is no longer in use, the Ruby garbage collector will destroy it and free up its space in the heap so that it can reuse it in the future. So once you've performed garbage collection, your heap is going to look a little bit like this slide. It's going to have some slots that are full with objects. It's going to have some free slots. And you would think that once this happens, Ruby can reuse those free slots in order to allocate more objects and keep running your program. However, it is not this simple. So Ruby can only reallocate used heap pages once they are completely empty. The empty slots that exist on heap pages that still have some stuff in them are not reusable. This can create a problem that is known as memory bloat. Memory bloat is when a program has allocated way more memory than it's actually like filling up with data. And so like according to your computer, your program may be using pages and pages and pages of memory on the heap, but those pages might only have 1 or 2 slots full. And in the absolute worst case, it could be like this example on the slide where you have heap pages upon heap pages allocated, but only 1 slot on each of those heap pages that is actually being used. So this is where memory compaction comes in. Using memory compaction, you can compact all of the used memory to the start of the heap, which frees up space at the end of the heap so that that memory can be reallocated. And you can imagine if you have like 1 heap page's worth of memory scattered across multiple heap pages, and then you condense that into 1 heap page. That's that frees up those heap pages at the end of the heap to be reused, which is fantastic. So this is what gc.compact does. gc.compact is a method introduced in Ruby 2.7 that implements memory compaction. This method has been called manual memory compaction because unlike garbage collection, which just runs by itself in the background, you actually have to call this method yourself. So manual memory compaction. Just to recap what I've learned so far in this process. So Ruby objects take up space in memory in part of the memory called the Ruby heap. Garbage collection automatically deletes objects that are no longer being used in order to free up memory. However, free memory can't always be reused because it's not all contiguous slots at the end of the heap. So memory compaction is a process by which in-use memory is grouped into contiguous chunks at the start of the heap, that way freeing up the end of the heap to be reallocated for use later in the program. So this is all well and good, but, oh, sorry, it did not answer my question. Why was gc.compact causing a seg fault? And I can confirm this is what I look like when I'm angry. You do not want to see it. It is not good. Luckily, a different user came to my rescue and left a comment on the ticket along the lines of, hey, have you read this page about using gc.compact with C extensions? Needless to say, I had not read that page. And so I did. You'll remember that I mentioned at the beginning of the talk that the BSON gem has a C extension. It turns out that this is actually really important when it comes to compatibility with memory compaction. So for some background, a C extension is C code that's integrated into a Ruby gem. You can use a C extension to include like a pre-built C library into your Ruby gem if you don't want to like rebuild some functionality that's already out there. Or you could implement some feature from your Ruby gem in C for increased performance or to like take advantage of some feature of the C language that you really want to use. C extensions are cool because you can create and manipulate Ruby objects in C code using the C extension API provided by the Ruby maintainers. So this is an example of creating a string with the value hello in both Ruby and C. So the first line is just plain Ruby. The second line is the C equivalent. So you start by saying the type of the variable you're creating. In this case, it's value, and I'll explain what that is in a minute. The name of the variable is greeting. And then you use a Ruby C extension method, RB string new2, that creates a new Ruby string, and then you pass it the value that you want the string to have, which is hello. So that's how you create a new string from a C extension. Like I said, we are going to use a variable type called value. A value is a pointer to a Ruby object. So remember earlier how I said that every slot in the heap has an address. Well, this is where that comes back. A pointer is a variable that contains the address to some slot in the heap. So when you create the greeting variable, what you're doing is essentially creating a variable that is storing just the address to on the heap. And it's saying, I know that there is a string there and at the heap address to. Then anytime that you use the greeting variable in your C code, what you're essentially saying is, hey, go get me that thing that lives at heap address 2. And that's how, you know, a lot of C code and like code in other languages that use pointer references is written. You could even use this same logic to declare new Ruby types. This is why C extensions are so cool. So this is an example that I took from a great article by Josh Haberman. I will make sure to post these slides in the Slack channel at the end, just so you can click through these links and take a look at this article. But in this article, we create a new type called a Ruby pair. So a Ruby pair, it just has two references to two other Ruby objects. We call those objects first and second. And those references are values, which means they are pointers to two locations on the heap. So in this case, you know, you could declare a Ruby pair and have the pointer to the first object be on heap slot 1 and the pointer to the second object be at heap slot 4. This is awesome, right? Because it's really flexible and you can extend the Ruby language in a really powerful way. However, it creates some complications when it comes to things like memory compaction. So if you remember, memory compaction has the effect of moving things around in the heap. If you think a little bit more closely about this, this could be a major problem when you're writing code with pointers where you're basically just referencing addresses in the heap and hoping they contain the right objects. So let's go back to our Ruby pair example. If you'll remember, a Ruby pair contains two objects called first and second, and those objects are at positions 1 and 5 in the heap right now. So let's say that we run memory compaction and our objects move around in the heap. Suddenly, the reference in our Ruby pair is wrong. The object that we called second used to be at position 5. Now it's at position 4. And so whenever the Ruby pair goes to reference that object, one of two things is going to happen. The first and best case scenario is that your program's going to crash, either because there's nothing in the heap at that location, or whatever is in the heap at that location is so incompatible with whatever you're trying to do that your program segfaults and stops running. The worst case scenario is if you have another object in that location at the heap and it doesn't crash your program, and your program keeps running with this silent bug that eventually is going to return wrong data to your users or otherwise mess up your gem. This is the absolute worst case scenario. This could be really, really bad. And I'm imagining a C extension going, wah ha ha ha. So I realized this must be what was happening in my BSON gem. Some object somewhere is moving around during memory compaction, and future references to it are being broken because it is not where the program expects it to be in memory, and that causes a segfault. So how can I figure out what object is causing this problem? In order to do this, I first had to learn more about how Ruby manages memory from the perspective of a C extension. So the major thing you need to know is when you create a C extension, there are two scenarios where you have to tell the Ruby garbage collector how to properly garbage collect your objects. The first scenario is when you create a new Ruby type, like our Ruby pair example. So our Ruby pair references two objects. They're called first and second. At the C level, the C code understands these references. So it knows that a Ruby pair references these two objects. However, at a Ruby level, the Ruby garbage collector does not know about these references, and that can cause some very wonky behavior. Let's imagine that the Ruby garbage collector is running garbage collection, and it's going to mark the Ruby pair object because it's still in use. If it doesn't know about the references to the first and second objects from that Ruby pair, it could sweep them thinking they're no longer being used by your program. And then when you go to reference them the next time, there's nothing there in memory, or like I said earlier, there's something else there that could cause a silent bug and really, really mess up your program. So this is the kind of thing that would cause a segmentation fault. Luckily, the Ruby maintainers anticipated this because they're very smart, and they provided a way to prevent this from happening. And that is called mark callbacks. So a mark callback is a method that gets called every single time your new Ruby type gets marked during garbage collection. It tells the Ruby garbage collector how to mark related objects in order to not break your program. So this is an example of a mark callback for our Ruby pair. And you'll see the two last lines of the method call the method rbgc mark on the first reference and then the second reference. This is an important method, and it is going to come back later. So once we've implemented this mark callback, Ruby knows about the reference between the Ruby pair and the first and second objects. And so after it marks the Ruby pair object, it knows how to mark its two references as well using the rbgc mark method. And it's a great day to be a Ruby programmer. Another scenario in which you want to make sure you are properly marking an object in a C extension is if you have a long-lived object. What I mean by that is, let's say you create an object in your C extension initializer. This is a method that gets called when your C extension is loaded for the first time. So say you declare a variable in there, and then you want to use it later on in your C extension. Oops, sorry about that. If Ruby doesn't know about this, it could garbage collect this object, and then when you try to reference it later, your program breaks. This is why you want to use the rbgc register mark object method to mark a long-lived variable as a root object during garbage collection. This way, Ruby knows not to garbage collect it, and once again, it's a great day to be a Ruby programmer because your program is not going to break. So, as it turns out, how you mark your objects in a C extension is really important to memory compaction, and this is going to explain why. So let's look at the way that gc.compact is actually implemented in Ruby 2.7. There are 4 steps. The first is garbage collection, and I'm going to give you a hint that something happens here that helps prevent the kind of issue we saw earlier where memory moves around and then you have a seg fault later on. The second step is to move objects and collect them at the start of the heap. The third step is to just update any references to those moved objects so that you're not referencing objects that are in a different location. And then the last is another round of garbage collection to clean up anything that's left behind. So, like I said, something special happens during this first round of garbage collection. And that's because the Ruby maintainers did something important in Ruby 2.7 to make it compatible with existing C extensions. So, of course, they realized that objects would move around in memory and break C extensions. So it was really important for them to safeguard against this kind of thing happening. In order to do this, they changed the behavior of the existing C extension API so that marking an object when you run garbage collection also pins it in memory. You can think of pinning as like you pin a piece of paper onto a board. You know, that paper is not going anywhere. So an object that's pinned in memory is not going to go anywhere. And this is what's happening when you mark an object in Ruby 2.7. So if you remember our friend, rbgc mark, a great method, this is the method that was modified to also pin objects in addition to marking them. So let's go through our garbage collection with the addition of pinning. So if we take an example of a Ruby pair, it has 2 references, as we've said, a first and a second object. First, the Ruby pair object is going to be marked, and it will also be pinned in memory. Then it will mark its first reference and also pin that in memory, and do the same for its second reference. Then, when all is said and done, those pinned objects in memory are not going to move. And so when the Ruby pair goes to reference them in the future, they will still be there, and memory compaction will not have broken your program. So going back to like the bigger picture, the implementation of gc.compact, when you do that first round of garbage collection at the very beginning of the compaction process, you are pinning objects in memory that are still in use so that they do not move around and they do not break your C extensions. This gave me all the information I needed to figure out what was going on in my gem. Ruby garbage collection pins all marked objects in Ruby 2.7. This we know. Any object that is pinned does not move around in memory. Some object in my gem is moving around in memory, which means that it must not be getting pinned, and thus that it must not be marked. And so, as I said earlier, there are 2 cases in a C extension where you want to make sure you mark an object. That is, if an object is long-lived, or if an object is a reference from a custom Ruby type. As it turns out, a long-lived object that was not properly being marked was the culprit in the BSON gem. So if we look in the BSON gem, BSON C extension initializer, there is a line that declares a variable called RB-BSON registry, which is just a module that's defined in the Ruby gem. we never marked this variable or this object. And I believe that historically that was okay because I don't think that modules get garbage collected. Someone might correct me on that, but that's okay. But once you introduce memory compaction, it starts to be a problem because even if it's not being marked, then it's not going to stay in the same place and it's going to cause set faults. So in order to fix it, I used rbgc register mark object to mark it as root so that it is pinned in memory and it cannot move around, which fixed the gem. So everything that I've covered so far has kind of been maintaining compatibility with an older C extension as you're transitioning to Ruby 2.7. But this doesn't take full advantage of memory compaction, right? If you're pinning objects in memory, it means that you can't move them to the start of the heap, which means that there are going to be objects hanging around in your heap pages, and those heap pages can't be reused. So if you're creating a gem with a C extension where you just plan to use it with Ruby 2.7 and newer versions of Ruby, then you can take some different steps that will allow you to take full advantage of memory compaction. So the first thing is you want to use rbgc mark no pin. I think this method name has been changed to rbgc mark movable since Ruby 2.7. So like we said, rbgc mark was modified to not move objects in memory, to pin them in memory. And so we're going to use a different version of this method that just marks them and does not pin them. Then we're going to implement a new callback, much like our mark callback that gets called every single time an object is marked. We are going to implement a compaction callback, which gets run every single time an object is going to be compacted. So what you want to do is make sure that you can update the references in your object so that you know what their new location is in case they've moved. And to do that, you use the rbgc new location method in a very similar way that you would have used rbgc mark in your mark callback. I learned two main things from this process. The first is that systems design and understanding system design can be just as important as coding. In this case, I was a perfectly adequate coder, but because I didn't understand how Ruby memory management was implemented and the high-level design thinking behind that, I was having a hard time fixing this bug and doing my work. So sometimes those things can be just as important as being a good coder. And then the second thing that I learned is that knowledge sharing is absolutely crucial. If people hadn't written the blog posts or made the videos that they had, I wouldn't have been able to read them and I wouldn't have been able to fix this bug. And so you never know when the knowledge you put into the world is going to get someone else out of a big jam. And so if you're thinking about, writing a blog post or making an informative video and you have any doubts about it, I would say always do it, because the more knowledge we share with each other, the more we're going to empower each other and the better developers we're all going to become. These are my sources. Like I said, again, I will post these slides in the Slack so that you can click through these links and read these awesome articles. And just to summarize, Ruby 2.7 includes a manual memory compaction method. To maintain compatibility with older C extensions, make sure you're properly marking long-lived objects and their and references from any custom Ruby types that you create. And to implement a new C extension, you can use the rbgc mark no pin method and make sure to add compaction callbacks to your custom Ruby types. Lastly, nothing is impossible if you believe in yourself and your 1,000 browser tabs. Thank you very much. There might be a couple minutes for Q&A right now, but I will be taking questions in the Slack channel, and you can always reach me on Twitter if you would like. Awesome. So Rose asks, do pins need to be removed or managed later on? So I believe that they are automatically handled in the garbage collection process, like they are removed at some point. So you as a user don't need to do anything, and the Ruby maintainers have like built that into the process of garbage collection.
Right, we have time for one more question.
Awesome. Angela asks, how long did this entire investigation take? So I don't know if I'm embarrassed by this. It definitely took like a couple weeks, just because I think I wasted a lot of time flailing about uselessly, which is just like not a helpful way to debug anything. And so I was really down on myself. Like, I don't know how to fix this bug. I don't know anything about C extensions. I don't know anything about memory management. And instead, I think I should have stepped back and said, okay, I don't know anything about memory management. Let's learn about that. And once I got to that step, then I was finally able to make some headway. And then it took maybe like a week from that point of just like reading and trying to piece everything together. Awesome. I think that's all we have time for, but please ask your questions in the chat and I'll see you later. Thanks so much for coming, y'all.
All right. Thank you, Emily. All right, so we are now moving into our next big break for the day. Coffee service is available. It's right down the hallway for each and every one of you. Tea service relatedly, we've actually done a really good job with catering services this year. Every single person has exactly what's in their own fridge. So thank your local organizer. Let me tell you what, thank your local organizer, okay? All right, with that being said, like I said, we are heading into another break. Talks are going to resume here at 1:50 Central Time, which from about now is, if I have my time right, 1:50 Central Time. I am not doing the math today. But with that being said, check out Slack, participate in the communities, head over to Emily's Talk channel. If you've got any additional questions, she's going to be there to answer those. And with that, we'll see you soon.